I think कल जब class खत्म हुई, there were some students who were having doubts. So we can take up those doubts now.
Good afternoon, ma'am.
Good afternoon, बच्चे विशाल. So let's start the class. Yesterday we were talking about the what would be your intensity after n number of reflections if alpha bar is your average absorption coefficient. And I think some students were having doubt there, so I'll just start from there. So let's say you had an initial surface, and this is another surface, this is another surface, and let's say this is another surface. So by definition, we defined absorption coefficient as the sound energy absorbed by an object divided by sound energy that was incident on that object. And basically energy and incident, they are related to each other, right? So rather than talking about energy, you can talk in terms of intensity also. So that means if I want to talk about how much sound energy is absorbed by any object, what I have to do is that, let me write it in short form, absorbed energy would be always equal to alpha times incident energy. So we said that, let's say your initial intensity was 1. And you do it yourself, just start with initial intensity I naught, and you will see that the results are going to be similar here. But for simplicity right now, I'm going to take your initial intensity to be 1. Let's say that alpha bar is the average absorption coefficient of room, which basically means that we can say that every object in the room has absorption coefficient alpha bar. So by definition here, the energy that will be absorbed by the first surface is alpha times incident energy. Incident energy we said is 1. So basically your absorbed energy will be alpha bar in this case. Incident minus absorbed will be your reflected energy. So we'll have 1 minus alpha bar as your reflected energy here. Now, if you talk about how much energy will be absorbed on this surface here. On this surface, the energy that will be absorbed is going to be absorption coefficient, again, multiplied by incident energy. And the incident energy for this surface is 1 minus alpha bar. So this much energy is going to be absorbed here. Now, if you go to the next surface here, which is your third surface here, this was your incident energy. This much energy is absorbed. So reflected would be incident minus absorbed energy, and you will have 1 minus alpha bar into 1 minus alpha bar, which would be basically equal to 1 minus alpha bar whole square. Now, if you talk about the next surface, which is your third surface here, on this third surface, this is going to act as incident intensity or energy. Out of this, alpha times incident energy is going to be absorbed. So which basically means that the energy that will be absorbed by this surface is going to be alpha bar multiplied by the incident intensity, which is given by this number here, 1 minus alpha bar whole square. Whatever would be remaining, that would be reflected further. Now for this surface here, this is your absorbed energy, this was your incident energy. Again, for this surface, if I do incident energy minus absorbed energy, I'll get the reflected energy. Right? You can take 1 minus alpha bar whole square common out. There will be 1 minus alpha bar, which will effectively be equal to 1 minus alpha bar whole cube here. You see a pattern here. After first reflection, it became 1 minus alpha bar. After second reflection, it became power 2. After third reflection, it became power 3. So if there are n number of reflections, so after n number of reflections, your intensity is going to be 1 minus alpha bar raised to power n. Now, this was when your initial intensity was 1. If your initial intensity is I naught, then after n reflection, your intensity is going to be I naught multiplied by 1 minus alpha bar raised to power n. So this was the concept that we are going to use in the derivation of Eyring formula. Let's start with the Eyring formula again.
Can you show the previous slide once?
Sure.
Thank you.
Okay. We said that statistically, it has been found that if you have a room which has volume V, capital V, I'm going to retain small v for velocity of sound. And if S is the surface area, the total surface area inside the room, then it has been found that, again, it's a statistical kind of observation, that your sound is going to travel on an average 4V upon S distance between any two successive reflection. So the distance between any two successive reflection, and this distance is distance traveled by sound. And the word successive here is important because we are talking about two consecutive reflections. So it could be your third and fourth reflection, or it could be your seventh and eighth reflection. So the distance that would be traveled will be 4V upon S. Now, if V is the velocity of sound, in that case, you know the distance, right? You know the velocity. Then you can calculate what would be time between any two successive reflections. That would be 4 times V upon S multiplied by the velocity of the sound here. Now, this, Ritu mute kar dijiye please sabko. This is basically, as you can associate this with the time period, right, between any two consecutive reflections here. And you know the relationship between time period and frequency. Frequency is how many number of times an event is happening in 1 second or per unit time, if you are measuring it in minutes or hours, in whatever units of time you are preferring them. So if I know what is the time between two successive reflections, then I can calculate what would be the number of reflections per second. That would be that would be the inverse of this, which would be basically SV upon 4V, right? Because this is basically your frequency and this was your time between any two successive reflections. Now, these are number of reflections in 1 second. Now, the number of reflections in time t. Would be simply SVT upon 4 times V. These many number of reflections are going to happen in time t. From the previous slide, we know that what would be the relationship between your intensity after a certain number of reflections and the initial intensity, right? So from here at time t, these many number of reflections happened, right? And now we are saying that if alpha bar is the average absorption coefficient of that room, then my intensity would be I naught multiplied by 1 minus alpha bar raised to the power number of reflections. And that number of reflections here are this number over here that we have calculated. How many would be your number of reflections, right? We said that after n reflection, your intensity is going to be I naught into 1 minus alpha bar raised to power whole raised to power n in that case. So similarly from there, I can say that after t, this is my intensity here. Let's rewrite it a bit here. Okay, let's first define the another term. Let's define the time. Now this time was randomly any time. Now if I specify this time to be equal to the reverberation time, where capital T is your reverberation time. We said that reverberation time is the time in which your intensity becomes to 1/1,000,000th of the initial intensity, which basically means that at t is equal to t, your IT would become equal to I naught raised to power I naught into 10 raised to power minus 6, right? This is basically 1/1,000,000th of initial intensity, right? So this would be your intensity. And this is the same expression on the right hand side. And now this t is going to be capital T, because now this is not any random time, because we have put the value of intensity for the time equal to reverberation time. Hence, I need to replace this random time with the reverberation time here. So I'll have 4 free. This is going to cancel each other out. If you take natural logarithm on both sides, you will have minus 6 ln of 10 here, and then on this side you will have svt upon 4v ln of 1 minus alpha bar. This would be your expression here, right? You know that ln of 10 would be equal to 2.3026, right? That is the value of ln 10. So if I plug in that value also, minus 6 into 2.3026.
Ma'am, can you show the previous slide, please, ma'am? I need to copy something.
Sure, sure.
Thank you, ma'am.
Yeah. Remember, from this expression, our main aim is to calculate the reverberation time formula. Eyring formula for calculation of reverberation time.
Ma'am,
Done,
this
ma'am, done.
was I naught minus alpha,
Where is I naught minus alpha?
जो हमने कल किया था IT is equal to I naught minus alpha नहीं था वो?
This one?
Yes, ma'am.
Okay. So if you take, I'll do I naught for just 1 or 2 steps. If you start with I naught here, you will get an I naught here, right? This is your incident. Now this is your absorbed. So your reflected would be incident minus absorbed. So you'll get I naught, you can take common out and you will have minus alpha bar here, right? So your I naught is going to come common from the whole expression of 1 minus alpha naught.
Okay, ma'am.
And you can do the similar for the next step also, right? Because then you will have I naught, the absorbed intensity will be I naught alpha times 1 minus alpha, right? And this is now your incident. This is your absorbed. So if you want to calculate your reflected, incident minus absorbed will be your reflected. And again, your I naught is going to come out here from both of them, because you have
Yes,
I naught
ma'am.
here and I naught here.
तो हम इसकी थर्ड रिफ्लेक्शन में इंसिडेंट हम 1 माइनस अल्फा बार होल स्क्वायर मानेंगे.
हाँ जी, because for this reflection, this is going to be your incident. जो आपके सेकंड से रिफ्लेक्टेड होगी वो थर्ड के लिए इंसिडेंट होगी, राइट?
Okay.
So this is equal to SVT upon 4V, and then you had ln of 1 minus alpha.
मैम
हाँ जी,
मैम आपने पीछे IT की जगह I0 into 10 to the power -6 लिखा.
here
हाँ मैम.
I'm saying when you are, this is for any random time t. So if your t is equal to reverberation time, and we define reverberation as time as the time in which your intensity becomes equal to 1 millionth of initial intensity. That is your reverberation time. So I'm putting T is equal to capital T here, and IT is equal to 1 millionth of initial intensity. Because our main aim is to calculate the expression for reverberation time. Similar, like Sabine gave a formula, now we are going to go towards a more precise formula for calculation of reverberation time. So that's why I had to put a special case here.
Okay मैम.
Hanji. Ayush.
Ma'am, I want to ask that, why you replace n by, like, in the previous slide?
Why did we?
Just can you go to the previous slide? So,
Hanji.
like here, 1 minus alpha bar raised to power n, like n is replaced by this S surface area velocity time upon fall.
Because
So, okay.
this is your number of reflections, right?
Okay. Okay.
So we said after one reflection, your intensity would be 1 minus alpha bar I. This intensity after one reflection is going to be I is equal to 1 minus alpha bar times I naught. After 2, it would be square. After 3 reflection, it would be power 3, and so on. So now I know how many number of reflections I'm talking about,
Okay.
right? So the
Yes,
number
yes.
of reflections, rather than putting 3, 4, 5 something, I have plugged in a different value for the number of reflections.
Okay.
From here, because we want to calculate T here, so we'll take everything else on the other side. So I'll have minus 6 multiplied by 4 multiplied by 2.3026. Denominator velocity, let's take velocity on the one side, and then I'll have 1 upon S ln of 1 minus alpha bar. So this would be now your expression here. This velocity of sound is approximately 1120 feet per second is taken to be. If you plug in, there has to be volume here also, right? Ye wali volume term hum bhul gaye. So we have to keep this volume also here. 4 times volume there. So if you plug in this value of velocity here, you will get T to be equal to minus 0.05 V S times ln of 1 minus alpha bar. And that is why, remember, while talking about Sabine's expression, I said that it matters if you are talking about FPS system, foot pound and second, or you are talking in your SI units, because the velocity of sound is there in this constant. If you take velocity of sound in meter per second, corresponding to 1120 feet per second, agar aap isko meter per second mein karte ho, it comes out 341.4 meter per second, I think. And then if you calculate your T, it would come out in minus 0.162 V S ln upon 1 minus alpha. This is called as your, and again, it is obvious because you are taking your velocity into meter per second. This means that here your volume has to be in meter cube, surface area has to be in meter square. When you are taking velocity into feet per second, that by default means that your volume has to be in feet cube, your surface area has to be in feet square. And this expression for reverberation time is called as Eyring formula. We'll see that. Okay, here is an interesting thing. You might see a minus sign here at first, and it looks like time can't be negative. But in the denominator, you have ln into 1 minus alpha bar. We said that your alpha bar is always going to be less than equal to 1. And if you take ln of something which is less than 1, it is going to be a minus number. So your minus minus would become plus, and your reverberation time would always come out to be a positive number here.
Ma'am,
हाँ जी बच्चे.
the case we have taken is for only 20 degrees Celsius. And can we apply it in any condition?
Then you can change the velocity accordingly here. The
Yes, ma'am.
velocity that you are taking,
Yes, ma'am.
you change it as per the temperature.
Okay, ma'am.
So this was your expression here as ln of 1 minus a or alpha bar here. Now, there, I don't know if you have heard, there is an expansion for ln of 1 minus x, which is basically minus alpha bar minus alpha bar minus alpha cube by 3. And this is called as Maclaurin series. ये आपका टेलर सीरीज का एक स्पेशल केस है. If your alpha bar is small, if your absorption coefficient is small, in that case, what you can do is that, let's first plug in the value here. You'll have minus 0.05 V as ln of 1 minus for this. Let's plug in the value minus alpha bar square over 2 minus alpha bar cube over 3 and so on. If your alpha bar is a small number, in that case, I can approximate this with minus alpha bar and say that higher order terms are going to be very small number. For example, if you have alpha bar, let's say 0.1, if you take square of 0.1, it's going to be 0.01. And then we can say that we can ignore the higher order term. And in that case, your T would come out to be 0.05 V alpha bar S, because now this minus and this minus would become plus, which was the expression that was given by Sabine. And this is many times also called as Franklin formula. So your Sabine formula is a special case of Eyring formula, right? When your absorption coefficient is small, while we are talking about limitation of Sabine's formula, we said that it is only applicable when your alpha bar is less than equal to 0.2. Again, it's not very sharp boundary. ऐसा नहीं है कि आपका 0.1999 पे तो आपका perfect हो and 0.02111 पे आपको हो कि ये तो absolutely wrong हो गया है. It's not that sharp line 0.20. Right? So for smaller value of absorption coefficient, if you calculate your reverberation time, either by using Sabine formula or by Eyring formula, you will get the similar results. But as your absorption coefficient starts to get higher, in that case, you will observe a difference in the calculation of reverberation time from Sabine formula and Eyring formula. तब आपके जो रिजल्ट्स हैं वो काफी डिफरेंट आने शुरू हो जाएंगे. सबीन का जो फार्मूला है वो आपका ओवर प्रेडिक्ट करेगा एंड दैट यू कैन सी फ्रॉम हियर इटसेल्फ, राइट? क्योंकि आपके डिनोमिनेटर में और भी टर्म्स हैं यहाँ पे जिनको आप इग्नोर कर रहे हो. अगर आप उनको इग्नोर नहीं करते तो आपका डिनोमिनेटर लार्ज होता, राइट? सो सबीन का फार्मूला जो है डिनोमिनेटर को स्मॉल कर देता है एंड हेंस आपका रेवर्बरेशन टाइम वो ओवर प्रेडिक्ट करना स्टार्ट कर देता है. That is the reason why Sabine's formula overpredicts your reverberation time for larger value of absorption coefficient.
एक्सक्यूज मी मैम
हाँ जी बच्चे.
मैम ये थोड़ा सा कंफ्यूज हो गया मैम ये आयरिंग्स फॉर्मूला ऊपर वाला है ना मैम
हाँ जी ये वाला जो है
नेगेटिव साइन है
ये वाला आपका आयरिंग फार्मूला है और जब आप इसको अप्रोक्सीमेशन में चले जाते हैं when you say that I am going to approximate this is equal to minus alpha तभी आपका सबीन फार्मूला हो जाता है.
ओके मैम दोनों फ्रैंकलिन और सबीन दोनों सेम है फॉर्मूला
दोनों सेम है. They are the same.
थैंक यू मैम
Now let's
मैम
do
ये
a
जो
com-
डिस्टेंस बिटवीन सक्सेसिव रिफ्लेक्शन आपने निकाला वो मतलब पहले से फैक्ट है.
हाँ जी it's a statistical observation कि on an average between two successive reflection this much distance will be traveled by sound waves. And again it's like statistical, so that means in some cases it might be slightly more, in some cases it will be less.
एक्सक्यूज मी मैम.
ओके
हाँ जी
मैम तो जैसे सबीन का एक वो था डिमेरिट की डिसएडवांटेज कि वो स्मॉल अल्फा के लिए पॉसिबल था.
हाँ जी वो
तो सर-
आपकी अब एलिमिनेट हो गई है आयरिंग फार्मूला में.
बट आयरन फार्मूला हमें सब अल्फा के लिए भी दे सकता है मतलब सारी वैल्यूज के लिए.
सारी वैल्यूज के लिए देगा.
ओके बस
I'm
इसमें
just-
एक ये लिमिटेशन है कि हमने उसे डिस्टेंस को एक माना हुआ है.
सबीन
Average.
के में भी बहुत सारी approximations थी that we didn't go into detail, right? Because for example Sabine said कि आपकी जो location of source and listener नहीं matter करेगा, right? And
Yes,
आपके जो objects की placement नहीं matter करेगी, which basically means that we are saying that your sound is very diffused in the room, as I said before. आप speaker के बहुत पास नहीं खड़े हो, which also means that. So there were approximations in Sabine formula also, right? Assumptions rather. We said that your Sabine formula, if you compare both of them, your reverberation time is going to be good only if you take your alpha to be less than equal to 0.2. Or rather when your alpha bar is small. For large alpha bar, it's going to overpredict. That's what we saw in the previous slide, right? It's going to overpredict your reverberation time T. Eyring formula is applicable for all values of alpha. This is point one. Now let's talk about the extremes, right? We said that for larger value of alpha, it is going to overpredict this. What could be the maximum value of alpha bar? It could be equal to 1. We saw this expression before also. This would be your reverberation time, which is a finite number. But we know that if something is a perfect absorber, right, which basically means that it is going to absorb all the incident sound on it, then your reverberation time should be equal to 0. But Sabine's formula is saying that you will still get a finite reverberation time. Now, if you do the same with Eyring formula, you will get ln of 1, right? Okay, when you have ln of x and
ln of 0.
Oh, sorry, you will have ln of 0. Sorry about that. When you have ln of x, in the limit x tends to 0. Ln of 0 is kind of undefinable, but in the limit x tends to 0, your ln of x would be infinity. And in that case, you will get your reverberation time to be equal to 0. And that is what should have happened in the case of a perfect absorber, that your reverberation time should become equal to 0. If you talk about the another extreme, which is basically when your alpha bar is equal to 0, which basically means that now you have a perfect reflector. There is no absorption of sound. Everything that is falling on the surfaces is going to be reflected back. If your alpha is equal to 0, in that case, in the Sabine's expression, if you put alpha is equal to 0, your reverberation time becomes infinite. and which is what we should expect because there is no absorption. So sound is going to be reflected an infinite amount of time. In the similar case here, if you put alpha bar is equal to 0, you will have ln of 1 here, and ln of 1 would go to 0. Again, in the limit ln x, in the limit when your x tends to 1, you will have your value to be infinite here, value to be 0 in this case. And that would lead to your expression for this being also infinite. S multiplied by 0, and you will get your answer to be infinite here. So for the small absorption coefficient, we have taken the extreme, but if your absorption coefficient is again small, in that case, Sabine's formula as well as Eyring formula, they will give the similar result. But you will feel the difference when you start taking the absorption coefficient large. For example, take absorption coefficient to be, let's say, 0.4 and 0.5 for a similar size of the room. And then do your calculation for the reverberation time using Sabine and Eyring formula. Do that after the class, and then you will see the difference between your reverberation time in both of the cases. Now the last topic.
Ma'am, I copy the slide, ma'am. Just 2 minutes.
Sure.
Ma'am, I have a doubt.
Hanji, bache.
Ma'am, I just need a clarification. So what exactly do we mean by reverberation time? मैं थोड़ा सा confused इस मामले में baby. Do we mean the time it takes for the sound to leave the material, or do we mean the time like is it in a specific situation, or is it common to every situation? That's what I'm confused about.
So, for example, whenever if you have just a momentarily sound, right?
Yes,
and you can have a continuous sound also. So in the momentarily sound, whenever the source makes the sound from that point to the time when intensity becomes 1/1,000,000th of your initial intensity.
Right, ma'am.
That would be a reverberation time. If it's a continuous sound, so when that sound is stopped, you start your clock from that time onwards.
Okay, ma'am.
And from that time to the time, there is another way of measuring this reverberation time, that is in terms of decibels. It's defined as the time in which your intensity becomes to 60 decibels of initial intensity or something like that.
60% of initial. Thank you, ma'am. Thank you so much.
Not the 60%, 60 decibel. There is
60 decibel. Sorry.
Yeah, so it's this another definition. So now the last topic in this acoustics is, for example, you have any object and you want to measure the absorption coefficient of that object. How we can do that? So we are going to talk about one method for determination of absorption coefficient. How can we measure the absorption coefficient? And before we start that, there is a method in which I'm going to use this expression. So I would like you to store this expression somewhere in the back of your mind. I'm going to use this expression again in one of the methods that we are going to discuss maybe in the next class. So I'll start from this expression here. So I would like you to store this expression somewhere. So there are two ways to measure absorption coefficient. One is the reverberation chamber method. And the second is stationary wave method. We'll just talk about the reverberation chamber method. That's only part of your syllabus. Okay, and before we proceed further, the derivation of Eyring formula, it's not a part of your syllabus. But I just didn't want to give you, infinite number of formulas without any background. So that's why we did the derivation of this portion over here. Otherwise, in your syllabus, you just have to know the formula for the Eyring. So we are going to talk about the reverberation chamber method. As the name suggests, you simply have a chamber in this case. right? Usually labs में आपके पास एक chamber होता है, and then there are different techniques using which you can measure the reverberation, using which you can measure the absorption coefficient of any particular object. So there are further subsections here. There will be 3 different ways in which you can measure the absorption coefficient using the reverberation chamber method. We'll discuss all of the 3 ways one by one. So in the first way, what you do is that you measure the you have a chamber, and in that chamber you basically place the object for which you want to measure the absorption coefficient, and with that object you measure the reverberation time of the chamber. So what would happen is that if you talk in terms of expression, you will have yours something like that. And let's say that your chamber itself has some kind of absorbing power, which is given by this expression. And then with your object, right? Let's say that your object has an absorption coefficient of A and it has a surface area of SO. This would be now your reverberation chamber with the object here. Now what you, in the second step, what you do is that now you take out this object from your chamber. आप इस object को अपने chamber से remove कर देते हो. And then you start opening a window in that chamber till the time your reverberation time becomes equal to this number over here. Let me repeat that. फर्स्ट मेथड में आप क्या करते हो, आपके पास जो रेवर्बरेशन चैम्बर है, बेसिकली इट कुड बी एन आयरन चैम्बर, सिलेंड्रिकल हो सकता है आपका आयरन चैम्बर है, या रेक्टेंगुलर फॉर्म में आपका आयरन चैम्बर हो सकता है. उसमें आप क्या करते हो, आप अपना ऑब्जेक्ट उसके अंदर प्लेस कर देते हो. उस ऑब्जेक्ट के साथ में आप अपना रेवर्बरेशन टाइम जो है वो मेजर करते हैं. लेट्स से दिस केम आउट टू बी रेवर्बरेशन टाइम, जहां पे ये आपका चैम्बर का वॉल्यूम हो गया, ये आपकी चैम्बर की कुछ एब्जॉर्बिंग पावर थी, एंड ऑन द टॉप ऑफ दैट आपने जो नया ऑब्जेक्ट ऐड किया है, उस ऑब्जेक्ट की वजह से ये आपकी एब्जॉर्बिंग एडिशनल पावर हो गई उस चैम्बर की. Now in the second step, what you do is that you take out that object out of the chamber, एंड फिर आप चैम्बर में एक विंडो को ओपन करते हो. उस टाइम तक आप ओपन करते रहते हो जब तक आपका जो रेवर्बरेशन टाइम है वो इस रेवर्बरेशन टाइम के इक्वल नहीं हो जाता है. विच बेसिकली मीन्स दैट आप विंडो तब तक ओपन करते रहते हो जब तक उस विंडो की जो एब्जॉर्बिंग पावर है वो इस सेकेंड टर्म के इक्वल नहीं हो जाती है. राइट, लेट्स से आपने जो विंडो ओपन की उसका सरफेस एरिया SW था. जब आपने सरफेस उस एरिया की विंडो ओपन कर दी, राइट, यू स्टार्ट विद अ स्मॉल साइज विंडो, यू सी योर रेवर्बरेशन टाइम, एंड आपको लगता है कि आपका रेवर्बरेशन जो टाइम है वो अभी मैच नहीं हुआ है. यू कीप ऑन ओपनिंग द विंडो अंटिल यू अचीव दिस रेवर्बरेशन टाइम जो आपने उस ऑब्जेक्ट के साथ में किया था. विच बेसिकली मीन्स दैट वॉल्यूम क्योंकि आपका नहीं चेंज हुआ है चैम्बर का, चैम्बर की एब्जॉर्बिंग पावर भी नहीं चेंज हुई है. ओनली डिफरेंस हियर वुड बी कि अब आपने वहां पे एक विंडो ओपन कर दी है, विच मीन्स दैट अब आपकी जितनी एब्जॉर्बिंग पावर उस ऑब्जेक्ट की थी, आपकी विंडो की एग्जैक्टली सेम एब्जॉर्बिंग पावर होगी. रिमेंबर, विंडो हैज एब्जॉर्प्शन कोएफिशिएंट इक्वल टू 1. So this basically means that your AS naught is equal to SW, or I can say that your absorption coefficient is equal to SW over S naught, which is basically area of window divided by area of object. And क्योंकि विंडो की जो absorbing power है, हमने कहा है it has to be exactly equal to your absorbing power of the object. So now the area of window and object, they are not equal to each other, and hence you can measure the absorption coefficient of that particular object. जो आपने उसमें प्लेस किया था. So this would be your first method.
Ma'am,
हाँ जी बच्चे.
ma'am, just please explain how A S0 become equal to SW.
Okay. Because I'm saying that
Ma'am,
initially
ma'am, just can you show the previous slide of this? I just need one to see that.
previous slide.
Yeah, before this one. Ah, yeah. Thank you, ma'am.
Thank you. So this expression, आपका जब रेवर्बरेशन टाइम आपने दो तरीके से मेजर किया, एक बार उस ऑब्जेक्ट के साथ में किया एंड एक बार आपने विंडो के साथ में किया, राइट? सो हम कह रहे हैं जब आपने ऑब्जेक्ट के साथ में किया, ये आपके रेवर्बरेशन चैम्बर का एब्जॉर्बिंग पावर है एंड ये आपके ऑब्जेक्ट का है. सेकेंड टाइम में आपने विंडो के साथ में किया एंड आपका जो रेवर्बरेशन टाइम है, आपने विंडो का साइज एडजस्ट करते रहे जब तक ये जो सरफेस एरिया विंडो का इतना नहीं हो जाता है कि ये जो आपका रेवर्बरेशन टाइम है वो प्रीवियस रेवर्बरेशन टाइम के इक्वल आ जाए. Till that point you kept on opening the window.
Yes, sir.
Ma'am, I have a doubt.
Just a second, let me answer his question first. So if now your left hand side is equal on both sides,
yes, sir.
आपका न्यूमरेटर सिमिलर है, डिनोमिनेटर का एक कंपोनेंट सिमिलर है, so that means आपका डिनोमिनेटर का जो सेकंड कंपोनेंट है that also has to be equal to each other.
Okay.
हाँ जी बच्चे. Someone else had a doubt.
Yes, ma'am.
हाँ जी.
मैम जब हमने जब ऑब्जेक्ट रखा मैम, इसमें हमें तो ए की वैल्यू निकालनी है ना.
हाँ जी.
तो अगर हमारे पास ए की वैल्यू होगी नहीं तो हम टी कैसे निकालेंगे? पहले जब आपने बोला हमें पहले टी निकालना है.
क्योंकि आप उसको कैलकुलेट नहीं कर रहे हो, राइट? यू डोंट केयर उसका क्या एब्जॉर्प्शन कोफिशिएंट है. आपने रूम में ऑब्जेक्ट रख दिया, राइट? आपने वहां पे साउंड प्रोड्यूस कराई.
यस मैम.
फिर आपने क्लॉक से मेजर कर लिया कि आपकी साउंड की इंटेंसिटी कितने टाइम के बाद 1 मिलियन ऑफ इट्स इनिशियल इंटेंसिटी हो जाएगी.
अच्छा, मतलब वहां पे हम फिजिकली मेजर कर रहे हैं, फॉर्मूले से नहीं निकाल रहे.
हाँ जी, एग्जैक्टली.
हाँ जी. वो मैम मुझे लगा कि आप फॉर्मूले से निकाल रहे हो तो इसलिए मैं कंफ्यूज हो गया. वो
आप उसको फिजिकली मेजर कर रहे हो, राइट? सो विद दैट ऑब्जेक्ट यू मेजर फिजिकली द रेवर्बरेशन टाइम ऑफ द चैम्बर. आपका जो चैम्बर होता है इट्स वेरी वेल इक्विप्ड विद a source that is going to produce sound and a timing machine to measure the time also. दोनों उसमें आपके में होते हैं. तो आप फिजिकली रेवर्बरेशन टाइम जो है वो मेजर करते रहते हो साउंड के साथ में. तो आप पहले ऑब्जेक्ट के साथ में मेजर करते हो रेवर्बरेशन टाइम, फिर आप विंडो का साइज एडजस्ट करते रहोगे जब तक आपको सिमिलर रेवर्बरेशन टाइम नहीं मिल जाएगा. And that's how you get the absorption coefficient here. Now, the second method. In the second method, what you do is that you measure the reverberation time of the room with the object and without the object, right? Let's say that without जो object है, आपने अपने चैम्बर का reverberation time जो है वो आपने मेजर किया. लेट्स से दैट केम आउट टू बी दिस मच, राइट? अब फिर आपने क्या किया, उसमें अपना ऑब्जेक्ट प्लेस कर दिया. अब ऑब्जेक्ट जब आपने प्लेस किया तो क्या होगा, उसका रेवर्बरेशन टाइम चेंज हो जाएगा, राइट? क्योंकि आपका वॉल्यूम तो सेम है बट आपका जो डिनोमिनेटर है वो अब आपका चेंज हो जाएगा. अब डिनोमिनेटर में आपका क्या आएगा, जो ऑब्जेक्ट है उसका कितना सरफेस एरिया है एंड उसका क्या एब्जॉर्प्शन कोफिशिएंट है, राइट? लेट्स से आपके ऑब्जेक्ट का एब्जॉर्प्शन कोफिशिएंट A है, उसका सरफेस एरिया जो है वो S है. तो अब आपका जो रेवर्बरेशन टाइम है वो ये होगा. अगेन आप सिंपली बस टाइम मेजर कर रहे हो. यहाँ पे ये वाला टाइम आपने मेजर किया और ये वाला टाइम आपने मेजर किया. बिना ऑब्जेक्ट के सिंपली रेवर्बरेशन चैम्बर को क्लोज कर दिया. आपने वहां पे साउंड प्रोड्यूस कराई एंड फिर आपने लेट्स से कि टाइम मेजर किया कि कितने टाइम में आपकी जो इंटेंसिटी है वो 1 मिलियन ऑफ इनिशियल इंटेंसिटी हो जाएगी. फिर आपने चैम्बर में ऑब्जेक्ट को रख दिया एंड फिर से आपने वही स्टेप रिपीट किया. आपने साउंड प्रोड्यूस कराई एंड फिर देखा कितने टाइम के बाद आपकी जो इंटेंसिटी है 1 मिलियंथ ऑफ इनिशियल इंटेंसिटी हो जाएगी।
मैम इधर भी हम फिजिकली कर रहे हैं।
हाँ जी, ये भी आप फिजिकली मेजर कर रहे हैं, आप साउंड प्रोड्यूस करा रहे हैं एंड आप टाइम मेजर कर रहे हो। अब क्या होगा, ये आपके दोनों केसेस में रेवर्बरेशन टाइम जो आप मेजर करोगे दोनों केसेस में डिफरेंट होगा, क्योंकि जब आपने ऑब्जेक्ट डाल दिया विच बेसिकली मींस दैट आपने एक और मटेरियल इंट्रोड्यूस करा दिया जो कि साउंड को एब्जॉर्ब कर पाएगा, तो आपका रेवर्बरेशन टाइम जो है वो इस केस में रिड्यूस हो जाएगा एज कंपेयर टू द प्रीवियस केस। अब अगर मैं यहाँ से, मेरा मेन इंटरेस्ट है ए कैलकुलेट करना, राइट? इफ I do 1 upon T2 minus 1 upon T1 here. So I'll have alpha times S plus AS minus, oh sorry, there should be plus here because this is Sabine's formula. जागो बच्चों, सो नहीं क्लास में। रितु म्यूट कर दो सबको प्लीज, राइट? ये प्लस आना चाहिए क्योंकि मैं सबीन का एक्सप्रेशन यूज कर रही हूँ। आई वाज जस्ट यूजिंग माइनस एवरीवेयर, आप में से किसी ने देखा भी नहीं। सो ये आपका सबीन फार्मूला है, सो यू शुड हैव प्लस एवरीवेयर हियर। सो आपका जो अब एक्सप्रेशन होगा दैट वुड बी 0.05 V, 1 upon T2 would be this much minus 1 upon T1 which will be alpha bar S upon 0.05 V। डिनोमिनेटर दोनों में सेम है, आप फिर कैंसिल कर सकते हो। एंड लेट्स राइट फॉर ऑब्जेक्ट सरफेस एरिया SO, ताकि ये कंफ्यूजिंग ना हो, क्योंकि S वी आर यूजिंग फॉर द टोटल सरफेस एरिया ऑफ द चैम्बर, जो आपका विदाउट दैट ऑब्जेक्ट था। अब यहां से, हाँ जी,
इंटेंसिटी मेजर करने के लिए भी उस चैम्बर में कोई इक्विपमेंट होता है?
यस,
कि हमें पता चल जाए कि कब 1 मिलियंथ इंटेंसिटी हो गई है।
हाँ जी, हाँ जी।
ओके मैम।
सो आपका ये वुड बिकम इक्वल टू दिस 1 अपॉन T2 माइनस 1 अपॉन T1। आपका ये एब्जॉर्प्शन कोफिशिएंट आ गया है। अब आपको रेवर्बरेशन चैम्बर का वॉल्यूम पता है, अगर आपने जो ऑब्जेक्ट प्लेस किया है उसका सरफेस एरिया पता है, ये दोनों आपने एक्सपेरिमेंटली मेजर किए हैं T1 एंड T2, तो आप उस मटेरियल का एब्जॉर्प्शन कोफिशिएंट जो है वो कैलकुलेट कर सकते हो। This is the second method. Third method will start tomorrow. So anyone has doubts so far?
Ma'am, can you just go to the previous slide?
Yes, I can do that.
Ma'am, what is the second method called?
There are no names to these methods.
And
all these are parts of reverberation chamber method.
Okay, ma'am.
And ma'am, can you
क्योंकि
just take
तीनों
the,
methods जो हम डिस्कस कर रहे हैं उसमें आप reverberation chamber का यूज कर रहे हो।
ma'am, can you just take to that slide that where you have written logarithmic expansion of 1 plus alpha bar, 1 minus alpha bar?
Yes, this one you are talking.
No. Yes, ma'am. Yes, this one. Okay, ma'am.
So all the three methods, they come under the category. The third, we have discussed two methods. Third, I am going to discuss tomorrow. And all these three methods, they come under the category of reverberation chamber method.
Ma'am, can you please tell me the name of the book?
खन्ना एंड बेदी बुक है बच्चे, उसके एक्चुअल में क्योंकि वो बहुत पुरानी बुक है, वो इजीली अवेलेबल नहीं है, तो लाइब्रेरी की जो बुक थी उसके जो रेलेवेंट पेजेस हैं उसका स्कैन करके मैंने LMS पे डाला है।
ओके
मैम।
हाँ जी।
Slide of second method, please.
Okay. This is the second method.
मैम एक बार नेक्स्ट क्लास में सेकंड मेथड फिर एक्सप्लेन कर देना।
हाँ जी, सेकंड मेथड का क्या आप कुछ कह रहे हैं?
नेक्स्ट क्लास में एक बार सेकंड मेथड फिर से एक्सप्लेन कर देना।
हाँ जी, sure. We'll start from the second method in the next class.
मैम क्वेश्चंस कैसे फ्रेम होते हैं इसमें?
क्या होते हैं?
क्वेश्चंस कैसे फ्रेम होते हैं?
Okay. For example, इसमें आपका आ जाएगा जैसे हम 3 मेथड कर रहे हैं reverberation chamber method के. So discuss any 2 method of measuring the absorption coefficient of sound.
हम तो न्यूमेरिकल नहीं आएंगे इसमें?
न्यूमेरिकल भी आएंगे बच्चे, बट थ्योरी के इस तरह के होंगे. अगर आप गूगल करो ना यूपीएच 004 क्वेश्चन पेपर, देयर इज दिस I didn't know, I'm not sure if I'm going to spell it right. My Harupa, have you heard
Yes,
of
ma'am.
Yes, ma'am.
इस पे आपके
Ma'am,
यूपीएच
available
के,
है क्वेश्चन पेपर.
हाँ जी, इस पे आपके यूपीएच के पिछले 4-5 साल के क्वेश्चन पेपर्स हैं.
Yes, ma'am, है उस पे.
मैम एक्चुअली मैंने ढूंढे थे तो मुझे एंड सेमेस्टर के मिले थे, मिड सेमेस्टर के मेरे को मिल नहीं पाए.
अच्छा, आई थिंक कुछ एक मिड सेमेस्टर और ऑक्सिलरी एग्जाम भी थे. पैटर्न आपका एग्जाम्स का सेम रहता है एमएसटी और ईएसटी का, सिर्फ मार्क्स का ही डिफरेंस रहता है.
Ma'am, can we leave now?
हाँ जी, श्योर. जिनका हो गया है.
Thank you, ma'am.
Yeah, sorry about being late.
Thank you, ma'am.
Ma'am, is
Thank you,
there
ma'am.
is there any book from where we can practice questions?
Is there what, Bache?
Book, any book.
Is there what? I still didn't get you.
Book, ma'am. Is there any book from where we can practice questions?
On the acoustics, there is a book written by the professor from here itself. It's Physics for Engineers by N.K. Verma. That also has some questions. And this Khanna and Bedi also has some questions. So from any book of acoustics, you can try doing this.
Okay.
Ma'am, what is the name of the book, Khanna and Bedi?
A textbook of sound.
Okay.